According to the National Electrical Code, an equipment grounding conductor is required to be run in the service lateral between the utility pad-mounted transformer and the service disconnect. This requirement is detailed in NEC Article 250.112F, which stipulates that any service lateral exceeding 6 feet in length must include an equipment grounding conductor. It is important to note the equipment grounding conductor provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. The equipment grounding conductor ensures that metallic parts of the electrical system that are likely to become energized during a fault condition are properly grounded, minimizing the risk of electric shock. Now let us talk about overhead service entrance conductors. An equipment grounding conductor is not required to be run with the service entrance conductors between the service point and the service disconnect, provided the service is supplied via an overhead drop from pole-mounted transformers. This exception is outlined in NEC Article 250.112A, which specifies that an equipment grounding conductor is not necessary in overhead service entrance conductors when the grounded service conductor is metal enclosed. In this configuration, the metal conduit or raceway enclosing the overhead service entrance conductors effectively serves as the equipment grounding conductor. The conduit's connection to the grounding electrode system at the service point establishes a path for fault current to return to the source. Therefore, the meter case is grounded through its connection to the conduit. Let us elaborate further on Article 250.112F. It is crucial to understand why this provision exists. Underground service laterals are more susceptible to physical damage and corrosion compared to overhead services. The equipment grounding conductor provides an additional layer of protection, ensuring a reliable ground fault current path even if the grounded conductor is compromised. In situations where the service lateral is short, meaning 6 feet or less, the code permits an exception due to the reduced risk of a fault condition. However, for longer runs, the equipment grounding conductor is mandatory. The equipment grounding conductor must be sized in accordance with NEC Table 250.122. This table specifies the minimum size of the equipment grounding conductor based on the rating of the overcurrent protective device in the circuit. It is imperative to consult this table to ensure the equipment grounding conductor is adequately sized to handle potential fault currents. Let us look closer at Article 250.112A. This article focuses on overhead service entrance conductors and the conditions under which an equipment grounding conductor is not required. The key factor is that the grounded service conductor must be metal enclosed. This means the service entrance conductors are installed in metal conduit, such as rigid metal conduit, intermediate metal conduit, or electrical metallic tubing. The metal conduit provides a continuous, low impedance path to ground, serving as the equipment grounding conductor. It is essential that all conduit connections are made properly to ensure electrical continuity throughout the raceway system. The conduit must be securely connected to the service equipment and the grounding electrode system. The meter case, in this scenario, is grounded through its connection to the metal conduit. The conduit provides a path for any fault current that may occur in the meter case to flow back to the source, tripping the overcurrent protective device. This connection minimizes the risk of electric shock to anyone who may come into contact with the meter case. Now we will discuss the grounding electrode system. Both service lateral and overhead service configurations must be connected to a grounding electrode system. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, metal underground water pipes, or concrete encased electrodes. The grounding electrode system provides a connection to the earth, stabilizing the voltage of the electrical system and providing a path for fault current to dissipate. The grounding electrode conductor connects the grounded service conductor to the grounding electrode system. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. It is essential to ensure the grounding electrode conductor is properly sized and connected to the grounding electrode system. Now we will review some additional considerations. Firstly, it is crucial to consult the local electrical code in any applicable amendments. Local codes may have more stringent requirements than the NEC. Secondly, it is essential to use qualified electricians and engineers to design and install electrical services. Proper design and installation are critical to ensure the safety and reliability of the electrical system. Thirdly, regular inspections and maintenance are necessary to ensure the electrical system is functioning properly. Inspections can identify potential problems before they become major issues. And lastly, always prioritize safety when working with electricity. Follow all safety precautions and use appropriate personal protective equipment. Let's talk about the importance of proper grounding. Proper grounding is essential for electrical safety and the reliable operation of electrical equipment. A properly grounded electrical system minimizes the risk of electric shock, reduces the likelihood of equipment damage, and provides a path for fault current to flow back to the source, tripping over current protective devices. A proper grounding can lead to dangerous conditions, including electric shock, fire hazards, and equipment failure. Therefore, it is crucial to ensure that all electrical systems are properly grounded in accordance with the NEC and other applicable codes. It is worth reiterating that when dealing with underground service laterals exceeding 6 feet, an equipment grounding conductor is mandatory as per NEC Article 250.112F. This requirement ensures a dedicated low-impedance path for fault currents, enhancing safety and system reliability. In contrast, overhead service entrance conductors supplied from pole-mounted transformers do not necessitate an equipment grounding conductor if the grounded service conductor is metal enclosed, according to NEC Article 250.112A. The metal conduit or raceway in this scenario serves as the equipment grounding conductor, provided it is properly connected to the grounding electrode system. Let us consider the scenario where the overhead service conductors are not enclosed in metal conduit. In such cases, an equipment grounding conductor would be required to be run with the service entrance conductors. This is because the absence of a metal enclosure eliminates the inherent grounding path provided by the conduit. The equipment grounding conductor would then provide the necessary path for fault currents to return to the source. It is also important to note that the type of grounding electrode system can vary depending on site conditions and local requirements. Common grounding electrodes include ground rods, metal underground water pipes, and concrete encased electrodes, often referred to as UFA grounds. The selection of the appropriate grounding electrode system should be based on a thorough evaluation of the site and in accordance with NEC Article 250.52. Proper installation of the grounding electrode system is crucial for its effectiveness. Ground rods should be driven into the earth to a sufficient depth to ensure good contact with the soil. Metal underground water pipe should be used as grounding electrodes only if they are in direct contact with the earth for at least 10 feet. Concrete encased electrodes should be encased in at least 2 inches of concrete and located within the bottom 2 inches of the footing or foundation. In addition to the grounding electrode system, bonding is another important aspect of electrical grounding. Bonding refers to the connection of metallic parts of the electrical system to create an electrically conductive path. Bonding helps to equalize the voltage potential between different metallic parts, reducing the risk of electric shock. Bonding is required for metallic water pipes, gas pipes, and other metallic objects that are likely to become energized. The bonding conductors must be sized in accordance with NEC Table 250.102. Let's discuss the differences between grounding and bonding. Grounding refers to the connection of the electrical system to the earth, while bonding refers to the connection of metallic parts of the electrical system. Grounding provides a path for fault current to flow back to the source, while bonding equalizes the voltage potential between different metallic parts. Both grounding and bonding are essential for electrical safety and the reliable operation of electrical equipment. In summary, the NEC provides specific requirements for equipment grounding conductors in both service laterals and overhead service entrance conductors. These requirements are designed to ensure electrical safety and the reliable operation of electrical equipment. It is crucial to understand these requirements and to follow them carefully when designing and installing electrical services. Always consult with qualified electricians and engineers to ensure that the electrical system is properly grounded and bonded in accordance with the NEC and other applicable codes. Regular inspections and maintenance are also essential to ensure that the electrical system is functioning properly and that any potential problems are identified and corrected promptly. Remember, safety should always be the top priority when working with electricity. Therefore, understanding equipment grounding conductor requirements for commercial services is not just about compliance, it's about safeguarding lives and protecting property. Proper grounding practices significantly reduce the risk of electrical shock, equipment damage, and fire hazards. This knowledge empowers electrical professionals to design, install, and maintain safer and more reliable electrical systems. The complexities of the NEC, particularly Articles 250.112F and 250.112A underscore the importance of continuous learning and professional development in the electrical field. Staying up to date with the latest code revisions and best practices ensures that electrical work is performed safely and in accordance with the highest standards. Furthermore, understanding the nuances of grounding and bonding, including the selection and installation of appropriate grounding electrodes and bonding conductors, is critical for achieving optimal electrical system performance and safety. The information presented here serves as a foundation for further exploration and understanding of electrical grounding principles. It is essential to supplement this knowledge with hands-on experience, practical training, and ongoing education to become a competent and confident electrical professional. By prioritizing safety, adhering to code requirements, and continuously seeking to improve their skills and knowledge, electrical professionals can make a significant contribution to the safety and well-being of their communities. In closing, always remember that electricity is a powerful force that must be treated with respect. By following proper grounding practices, you can minimize the risks associated with electricity and create a safer environment for everyone. Keep yourself updated and consult with qualified professionals for all your electrical needs. The NEC guidelines are not static, they evolve to address emerging technologies and challenges in electrical safety. Regular updates and interpretations are issued to clarify existing rules and introduce new ones. Staying informed about these changes is crucial for electrical professionals to maintain compliance and ensure the safety of their work. Moreover, the application of NEC guidelines can vary depending on the specific context and jurisdiction. Local amendments and interpretations may exist, reflecting regional differences in electrical practices and environmental conditions. It is therefore essential to consult with local authorities and code officials to ensure that all electrical work complies with the applicable requirements. Beyond the specific requirements for equipment grounding conductors, the NEC addresses a wide range of electrical safety issues, including wiring methods, overcurrent protection, and equipment installation. A comprehensive understanding of the NEC is essential for anyone involved in the design, installation, or maintenance of electrical systems. In addition to the NEC, other standards and guidelines may also be relevant to electrical safety, such as those published by the Institute of Electrical and Electronics Engineers, Underwriters Laboratories, and the National Fire Protection Association. These organizations develop standards for electrical equipment, testing procedures, and safety practices. Compliance with these standards can further enhance the safety and reliability of electrical systems. The field of electrical safety is constantly evolving, with new technologies and challenges emerging all the time. For example, the increasing use of renewable energy sources, such as solar and wind power, has introduced new considerations for electrical grounding and protection. Similarly, the proliferation of electric vehicles and charging stations has created new challenges for electrical safety in residential and commercial settings. Staying abreast of these developments and adapting to the changing landscape of electrical safety is essential for electrical professionals to maintain their competence and ensure the safety of their work. Education and training play a vital role in promoting electrical safety. Apprenticeship programs, vocational schools, and continuing education courses provide opportunities for electrical professionals to develop their skills and knowledge. These programs cover a wide range of topics, including electrical theory, wiring methods, code requirements, and safety practices. Hands-on training and practical experience are essential components of these programs, allowing students to apply their knowledge in real-world settings. Furthermore, certification programs can help to demonstrate the competence of electrical professionals. Certification programs typically require candidates to pass an exam and meet certain experience requirements. Certification can enhance career opportunities and provide assurance to employers and clients that the electrician has the necessary skills and knowledge to perform their work safely and effectively. Public awareness campaigns can also play a role in promoting electrical safety. These campaigns can educate the public about the dangers of electricity and how to prevent electrical accidents. Topics covered in these campaigns may include the importance of ground fault circuit interrupters, the dangers of overloaded circuits, and the proper use of extension cords. By raising public awareness, these campaigns can help to reduce the number of electrical injuries and fatalities. Ultimately, electrical safety is a shared responsibility. Electrical professionals, employers, code officials, and the public all have a role to play in ensuring that electrical systems are safe and reliable. By working together, we can create a safer environment for everyone.